Hi, those on Zoom, can you hear me okay? Can you hear me?
Yeah, I can hear you.
Okay, great. All right, so mute your microphone for now. If you want to ask a question, you can unmute. And turn on the projector. Okay, welcome those on Zoom. We'll go ahead and get started here. Okay, I'm going to share my screen. Okay, so this class is on Zoom. It's also being recorded. First class session on Monday. That's under Panopto videos. This is on Zoom. So what I'm going to do, what I've done with my other class, is to make a new page on Top Hat, and on that page I'll have the links to the video recordings. Okay, so just very quickly to review, organic chemistry is the chemistry of carbon. Carbon has a number of unique properties, and we'll talk about those in more detail, but very briefly, carbon is able to form strong bonds with up to 4 other atoms, including other carbon atoms. There is a huge variety of different structures of carbon chains and rings and branch chains. There's about 10 million different organic compounds that are made. Okay, the first organic compound that was made in the laboratory was urea. And then we went on to look at the structure of the atom. Okay, and this is mostly a review. The atom consists of a nucleus which is small in size but contains the vast majority of the mass of the atom. The atom itself is 100,000 to 10,000 times greater in diameter than the nucleus. It depends on which element you're talking about. But most of the mass is in the nucleus. The nucleus consists of protons and neutrons. And we did a brief review of the different shells. These correspond roughly to rows in the periodic table. And then electrons exist in orbitals rather than orbits. Orbitals are 3-dimensional regions of space which define a certain probability of finding an electron. Orbits, on the other hand, are well-defined trajectories. Okay, but because of the Heisenberg uncertainty principle, we can't know the position and momentum of an electron at the same time. Okay, we can just define a probability of finding an electron within a 3-dimensional region of space. In this course, we're only going to actually look at the S and P orbitals. S orbitals are spherical in shape. P orbitals have two lobes. They're dumbbell or figure 8 shaped. Okay, so here we have the lowest energy orbital is the 1s. And each atomic orbital can hold 2 electrons. The electrons in the same atomic orbital have to have unpaired spins. That is, they have to have opposite spins is what I meant. Okay, so the 1s can only hold 2 electrons. So once it's filled, we start filling the 2s. That can only hold 2 electrons. The 2p, there are actually 3 2p atomic orbitals. They all have the same energy. We say they're degenerate, which means they have the same energy. When we fill the 2p orbitals, we fill each one with a single electron. So one electron goes in here, the next electron goes in here, and the third electron goes in here. When we get to oxygen, which is the 4th element in that series, okay, one of these has to be doubly occupied. Okay, so we'll have 2 in here, 1 in here, 1 in here. Okay, when we get to the end of the row, okay, that would be neon. And neon is a noble gas. It has all of its p orbitals filled. Okay, in fact, that's what is characteristic of all the noble gases. They'll have filled p orbitals. And the noble gases are noted for their exceptional stability, lack of chemical reactivity. Okay, and then once the p orbitals are filled, then we go on to the next row of the periodic table, and 3s would be sodium. Okay, and then we continue on. Okay, we won't be covering the d orbitals in this course. Okay, electrons have to have opposite spins if they're in the same atomic orbital. Okay, so this is a summary of what's called the Aufbau or building up principle. Okay, filling of electron shells, and okay, so we fill up the first period, which is hydrogen and helium, and then then the next one ends with neon. This shows a helium, well, it shows 2 different versions. There's the 1s, for example, for lithium, we have 1s2, 2s1. But the 1s2 for lithium really doesn't affect the chemical reactivity. It's the outermost electrons. Okay, so lithium and all of the other elements in that column will all have one outermost electron or one valence electron. So it's the valence electrons that determine the chemical reactivity. Okay, so outside of this noble gas core, we have the number of valence electrons. Okay, so fluorine, for example, would have 7 valence electrons. It's atomic number 9, but it has 7 valence electrons. Okay, and then the next core is neon. Okay, this also shows, this chart also shows how we populate the p orbitals one at a time. P orbitals have the same energy, they have the same size, they have the same shape, but the way in which they differ is that they are pointed at different directions in space. Okay, they're all they're all 90 degrees apart from each other. It's very convenient to line them up along an XYZ coordinate system, and that's what's been done here. Okay, we call this one the PX, 2PX. It's lined along the x-axis. Okay, and then the next electron would go in the 2py. Okay. Okay, because these electrons in different orbitals would have a better chance of avoiding each other than if they were in the same orbital. Okay, electrons all have a negative charge, they repel each other, they want to be as far apart as they can get. All right, and then what I was saying before, the third p electron goes into the pz, and then we start doubly occupying the 2px and then the 2py. And then neon, which is a noble gas, has all of the p orbitals filled. Okay, so here's an example problem. And okay, looking at the periodic table, we can write the ground state electron configuration of each element, given its atomic number and the relationship between the atom's ground state, electronic configuration, and its position in the periodic table. Okay, so magnesium is element number 12. Okay, the first row has 2 elements. The second row has 8. And so the neon core would consist of 10 electrons. And so there's 2 electrons beyond that. Okay, so magnesium would have 2 valence electrons. Argon is actually at the end of that row, and so we would show argon as having 8 valence electrons. It's got a filled valence shell. Okay, the valence shell is the outermost electron shell of each atom. Okay, and then the valence electrons are the number of electrons in the valence shell of an atom. Okay, these electrons are used to form chemical bonds. Okay, so we can look at the periodic table and we can determine the number of valence electrons by the position in the row. Okay, for example, carbon is the 4th one in the row, so it has 4 valence electrons. And then nitrogen is after it, it has 5, and so on. Okay, you're probably familiar with Lewis dot structures. We draw the symbol of the atom, and then we use dots to represent how many valence electrons there are. Okay, and so here we have some examples of Lewis dot structures. Okay, so here is, so hydrogen has 1 valence electron, so we draw a single dot. Helium is at the end of the row. Okay, we would show 2 dots for it, and then the next row, we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then the same way for the third row. Okay, for the 4th row, we have the 10 transition elements in there. As far as counting valence electrons, we would skip over the 10. And so the elements, the element below phosphorus, for example, which is arsenic, that would also have 5 valence electrons. Okay, so we'll look at some models of bonding. Okay, this is an important concept in organic chemistry as well. Okay, so atoms bond together so that each atom in the bond acquires the electron configuration of the noble gas nearest it in atomic number. Okay, the noble gases are exceptionally stable, so in bonding, atoms try to achieve a noble gas configuration. Okay, if an atom loses electrons, it becomes a cation. Okay, if it gains electrons, it becomes an anion. Okay, so there were two sodium atoms walking down the street. One of them says to the other, "I lost an electron." The other one says, "Are you sure?" "I'm positive." Okay, when an atom gains an electron, it becomes negative, and it becomes an anion. Okay, we'll talk about ionic and covalent bonding. In an ionic bond, we have two oppositely charged particles, and they attract each other through electrostatic forces. In a covalent bond, we have two atoms that are sharing one or more pairs of electrons. Okay, and we'll be dealing with chemical bonds that are ionic, that are polar covalent, non-polar covalent, and this will be based on the difference in electronegativity. Okay, so we can make predictions about which sort of bond we're talking about. Okay, so what is electronegativity? Electronegativity is a measure of the force of an atom's attraction for its electrons it shares in a chemical bond with another atom. Okay, so electronegativity is the ability to attract and hold electrons. Okay, here's an abbreviated periodic table. The most electronegative element is fluorine. And the least electronegative element, at least on this table, would be potassium. Okay, below potassium we have rubidium and then cesium. So cesium is the least electronegative element, and then below that is francium. It's a short-lived radioactive element. It's hard to measure its electronegativity, but it's probably in the neighborhood of cesium. Okay, so cesium, which is two elements below potassium in that first column, okay, has one outer electron, and that outer electron is very loosely held. Okay, it's like the fluff on a dandelion. The nearest breeze and it's gone. Okay, and then in this corner with fluorine, these elements have a strong tendency to hold on to electrons, to attract and hold electrons. So fluorine is the most electronegative, and then oxygen, and then third, it's very close between nitrogen and chlorine. Okay, there are periodic trends. Okay, as we go across a row from left to right, electronegativity goes up. As we go up a column, electronegativity also goes up. Okay, so for example, oxygen is more electronegative than sulfur. Oxygen is more electronegative than nitrogen. Okay, so we can make comparisons in electronegativity just by the position on the periodic table, the relative positions on the periodic table. Okay, there's several different electronegativity scales. This is one that was developed by Linus Pauling. And in this scale, fluorine is assigned a value of 4. Okay, oxygen is the next most electronegative. It's 3.5. And then over here, we have elements with really low electronegativities. Okay, less than 1, 0.7, 0.8, and so on. Okay, and these are color-coded. The ones in dark green are the least electronegative. The ones in this reddish color are the most. And then carbon is intermediate. Okay, and so is hydrogen. Okay, so to determine whether a bond between two atoms is ionic, nonpolar covalent, or polar covalent, we can estimate that based on differences in electronegativities between the two atoms in the bond. Okay, and this distinction is somewhat arbitrary. It doesn't suddenly jump after we get beyond 1.9. But if the difference in electronegativity is, say, less than 0.5, okay, then that would be a nonpolar covalent bond. Okay, so going back here. Okay, let's see if we can find a difference here. Okay, iodine monobromide, IBR. Okay, that would have a difference of less than 0.5. Okay, that's a covalent bond. Okay, the difference is 0.3 in electronegativity. Okay, and then if it's approximately 0.5 to 1.9 in difference, then we say that's a polar covalent bond. Okay, so going back here, okay, if we take ammonia, which is NH3, we've got a nitrogen that's bonded to 3 hydrogens. That's a difference of 0.9. Okay, that's a polar covalent bond. Those elements that exhibit covalent bonding are typically nonmetals or perhaps metalloids. Okay, so again, going back to this periodic table. Okay, over here on this side of the periodic table, okay, we have the metals, and then we have a stair-step line that occurs that separates the metals from the nonmetals, and nonmetals are on the right. And then we have some that are just right along this boundary that have some metallic properties and some non-metallic properties. And these are called metalloids or semi-metals. Okay, and that would include silicon, silicon here, arsenic, tellurium, Te, germanium, which is right next to arsenic. Okay, here's germanium. Okay, these right along the boundary, these are semi-metals or metalloids. Metallic properties include being a good conductor of electricity and heat. Metals are typically shiny, they have luster. Most of them can be hammered into sheets. We call that malleable, ductile. They can be drawn into wire. Whereas some of these metalloids, like silicon and arsenic and germanium, they do conduct electricity, but they conduct it poorly. Okay, which actually makes them useful as semiconductors in the electronics industry. Okay. So if it's between two nonmetals, or a nonmetal and a metalloid, it's probably a covalent bond. Okay, and then we can determine whether it's polar covalent or nonpolar covalent. based on the difference in electronegativity. Hydrogen is considered to be a nonmetal. Okay, if it is greater than about 1.9, then it's an ionic compound. Okay, so ionic compounds are between elements that are widely separated in the periodic table. Okay, such as magnesium chloride, okay, MgCl2, or potassium bromide, or magnesium oxide. Okay, they're widely separated in the periodic table. Okay, they have large differences in electronegativity. Sodium chloride, okay, the difference between 3 and 0.9 would be 2.1, so that's greater than 1.9, that is an ionic compound. Okay, in an ionic bond, there's no sharing of electrons, but instead there's a complete transfer of one or more electrons. Okay, so a sodium atom has no charge. The fluorine atom has no charge. But when sodium transfers an electron to fluorine, okay, sodium loses an electron, so it becomes positive. Fluorine gains an electron, so it becomes negative. Okay, so a fluoride ion would consist of 10 electrons and 9 protons. So you have an excess of 1 electron. Okay, fluorine's atomic number 9. Okay, when this occurs, both the sodium and the fluorine now have a noble gas configuration. Sodium looks like neon. Fluorine also looks like neon. Okay, so sodium fluoride is an example of an ionic compound. And in bulk sodium fluoride, there are actually no sodium fluoride molecules. Instead, you have what's called a crystal lattice, where you have a three-dimensional set of packed ions. Okay, and in this particular example, each sodium ion is surrounded by 6 fluoride ions. Each fluoride ion is surrounded by 6 sodium ions. And some of the characteristics of ionic compounds include, most of them have high melting points. Okay, for example, sodium chloride melts at about 800 degrees Celsius. So high melting points. The solids don't conduct electricity, but the molten salts or the aqueous solutions are good conductors of electricity. Okay, because these ions can carry charge. Okay, the other main type of bonding is covalent bonding. And a covalent bond forms when electron pairs are shared between 2 atoms whose difference in electronegativity is about 1.9 or less. Okay, an example is the formation of a covalent bond between 2 hydrogen atoms. Right, well, hydrogen has an electronegativity of 2.1, and so if we bond 2 hydrogen atoms together, the difference in electronegativity is 0. Okay, and by sharing these electrons, okay, each hydrogen atom completes its valence shell. So it's like neon. Okay, we represent the individual atoms as a symbol with a dot, and then a shared pair of electrons, we represent that using a solid line. Okay, so we have a pair of electrons here, and we consider both of these hydrogen atoms as owning that pair of electrons. Okay, when this process occurs, okay, when a bond is formed, energy is released. So this is an exothermic process when two hydrogen atoms come together to form a hydrogen molecule. Okay, it's exothermic, energy is released, we have a negative delta H. Okay, so the hydrogen molecule is an example of a pure covalent bond. The electron pair is shared equally, but in a polar covalent bond, the electrons are shared unequally. Okay, so the more electronegative atom will have a greater share of that electron pair, and we can designate that using the symbol lowercase delta. Okay, delta minus indicates a partial negative charge. Okay, and then the less electronegative atom has a partial positive charge, which we show as delta plus. Okay, so here's an HCl molecule. And okay, we actually have a couple of different ways of designating polarity down at the bottom here. Okay, we have the delta plus and delta minus. Chlorine is more electronegative than hydrogen, so it has a greater pull on the electron pair. Okay, and chlorine has an electronegativity of 3.0. Hydrogen is 2.1. Okay, so chlorine has a greater share of electrons. We can also designate that polarity using this this arrow with the bar pointing to the more electronegative element. Okay, this is an electron paramagnetic map, and it uses the colors of the rainbow to show electron density. Okay, so at one end we have red. Red indicates a region of high electron density. Okay, at the other end we have blue or violet, which indicates a region of low electron density. And then the other colors, such as green and yellow, indicate an intermediate electron density. But it goes in the order of the colors of the rainbow. Okay, so around chlorine, we have a high electron density. Around hydrogen, particularly at this end, we have a low electron density. Very important part of this course is drawing Lewis structures. And to draw a Lewis structure, okay, we'll first determine the number of valence electrons in the molecular ion. Then we'll determine the connectivity or arrangement of atoms. First, connect the atoms by a single line. Okay, arrange the remaining electrons so that each atom has a complete valence shell. And we show bonding electrons as single lines, non-bonding electrons as pairs of dots. Okay, so I'm going to draw a couple of examples on the board. Okay, and you'll get used to bonding, common bonding patterns, so you don't have to go through all of these steps every time. Let's take a simple example like ammonia and H3. Nitrogen is in group 5 of the periodic table. Here we're counting the number of valence electrons. Hydrogen is the first one in the row, so it has 1. And then there's 3 hydrogens. Okay, so that adds up to 8. Okay, and then we have to determine the arrangement of atoms. With small molecules like this, there's only one way we can actually arrange the atoms. When you do the pushing electrons workbook, this has been done for you. It'll show you how the atoms are arranged, but nitrogen has to go in the center. Hydrogens always have to be on the outside. They can't be between 2 atoms. Okay, so we'll first connect these with single bonds. Okay, so we have 2 electrons in each covalent bond, so 2, 4, 6, but we need 8. Okay, so the remaining 2 we'll put on the nitrogen. Hydrogen can only hold 2 electrons, so we can't put any on the hydrogen. Okay, this is an ion that those of you that took Chem 2 over the summer, we used this one in the equilibrium experiment where we complexed it with iron. Okay, so the thiocyanate ion, the atoms are in this order, so it's SCN. S is in group 6. Okay, it's right below oxygen. It's the 6th one in the row. Carbon is in group 4. Nitrogen is in group 5. And what do we do about the negative charge here? Add. Good. We add an electron. Okay. If it were positive, we would subtract. Okay. So this adds up to 16. The atoms are connected in this order. Okay, you might not know that without, and there actually are different ways of arranging the atoms in this particular example. We will first connect them with covalent bonds. Okay, but that only takes care of 4. We need 16. Right, so what we do is we start from the outside and we start filling out the valence shells. Okay, so nitrogen, we've got 2, 4, 6, 8. Okay, we can't have more than 8. Sulfur, we've got 2, 4, 6, 8. Okay, that is 16, but we're not finished yet because something we'll talk about shortly, and that is the octet rule. Carbon doesn't have a filled valence shell. And so the way that we can solve that, okay, last bullet point there, we can share more than one pair of electrons. Okay, we can't add or subtract because we've got our 16. Okay, but we can take these and we can make that a shared pair. Okay, carbon only has 6. Okay, so let's move a pair of electrons here. Okay, and okay, we got our negative charge. Okay, it turns out that there's actually more than one correct answer for this little structure. Okay, so if there is an ion, we need to subtract the appropriate number of valence electrons. Okay, so in a polar covalent bond, the more electronegative atom has a partial negative charge. The less electronegative atom has a partial, let's see, did I go backwards? Yeah, I went backwards. Okay. Okay, so here are some examples of Lewis structures of simple molecules. Okay, water has 2 bonding pairs and 2 non-bonding pairs on the oxygen. Here's HCl, hydrogen chloride. Methane has no non-bonding electrons, and then ammonia has 3 bonding pairs and 1 non-bonding pair. Okay, here are some examples of molecules that have multiple bonds. Okay, this is acetylene. It's C2H2. But in order to complete the valence shells of the carbons, we need a triple bond between the 2 carbons. This is ethylene with a carbon double bond. Formaldehyde. Okay, here we've got a carbon-oxygen double bond, and then carbonic acid. Okay, so here are some shortcuts. Okay, and these are important points to remember. In neutral molecules containing carbon, hydrogen, nitrogen, oxygen, and halogens. Okay, neutral is the key because if it's not neutral, then we'll have a different number of bonds. Okay, in a neutral molecule, hydrogen always has 1 bond and no unshared pairs of electrons. Carbon has 4 bonds. That can be 4 single bonds. It can be a double bond and 2 single bonds. It can be a triple bond and a single bond, or 2 double bonds. So some combination to give us 4 bonds. Nitrogen has 3 bonds, 1 unshared pair, okay, like ammonia. Oxygen has 2 bonds and 2 unshared pairs. And a halogen has 1 bond and 3 unshared pairs, okay, as shown in this example here. Okay, so here's an example. The halogen has 1 bond and 3 unshared pairs to complete its octet. Okay, so we have about 3 minutes remaining. I will touch on the concept of formal charge. Okay, an ion as a whole can possess a formal charge. In most cases, we can usually assign a formal charge to individual atoms. The sum of the formal charges of the individual atoms has to add up to the overall charge. Okay, and so to calculate formal charges, there's a couple of different ways of doing that, and I will illustrate one way, and that is to take the number of valence electrons in the neutral unbonded atom, and then we subtract the number of unshared electrons and 1/2 of the shared electrons. Or another way of saying that is the number of bonds. Okay, so unshared electrons, not unshared electron pairs, but unshared electrons and the number of bonds. Okay, so this is a good example here. I'll tell you that it's nitrogen that has the negative charge in this structure. So nitrogen is in group 5. We subtract we subtract the number of unshared electrons, which is 4, and we subtract the number of bonds, which is 2, and that adds up to -1. Okay, so nitrogen is carrying the -1 charge. Carbon has 4 bonds. Okay, so it has no charge. Sulfur has 2 bonds and 2 unshared pairs. Okay, well, we could actually calculate for sulfur. Sulfur has 6 valence electrons. We subtract the number of unshared electrons, not the number of unshared pairs, so that's 4. And then we subtract the number of bonds, and so sulfur has a charge of 0. Okay, and then we're out of time, so we'll pick this up again. Before we go, okay, I said in my email message, one of my email messages, that Friday lectures would be asynchronous or recorded. Okay, so that is the case. Okay, I'll notify you when the recordings are posted. Okay, so there'll be a link on top hat, and then for the recorded lectures, there'll be a few questions to answer, and there's points assigned for answering those questions. Okay, so that's it. Have a good day. I'll see you next week. Okay, so I'm going to stop sharing, and I'm going to end the meeting.